Yes, that's it. Does this work? Excellent at that. I'd like to thank the organizers, the opportunity to be here in Toronto. My younger daughter, when she had the pleasure of doing a exchange program briefly to Toronto from Chicago, described Toronto as just like Chicago, but cleaner. I don't know how she came up with that. So I'd like to celebrate a couple of things. One is we've seen that photograph out there on the table. People can correct me if I'm wrong. I think this is from about the 1920s, somewhere in the 1920s. Take a good look, and I also want you to look around the room here. Then I believe this is from the 1940s. So 1940s, a little bit of change on there. And then what I would like to celebrate, what's that? I'm assuming so. Yeah, I'm not sure exactly what. I'm just more intrigued by the collection of human beings in the picture. And then I'd like to celebrate something that happened yesterday in the United States. The 4 Black women who were part of the, quote, hidden figures in the NASA program in the 50s and 60s. The 4 of them were awarded the Congressional Gold Medal yesterday. Probably 60 years too late, but happy to report that Christine Darden is the one member of this group that is still alive. And so now I want to introduce you to integrated mathematical oncology. These are my peeps. So Bob Gatenby had the vision of bringing a mathematical oncology department to Moffitt. Sandy Anderson had a vision for what such a department would look like and has been our fearless leader in that department. These are the faculty in the department. And this is the group, hopefully a more interesting looking group of people than what we saw in the fields photographs at this point. And so we represent then a fairly big and hopefully growing number of faculty and postdocs, research scientists, and graduate students. So here's the imperative, I think, for cancer. And this is what motivates and drives a lot of my thinking in cancer. So this could be updated all the way to the present, but it really wouldn't change the trend. And most sources of mortality in the United States, in fact, in Europe and whatnot, the rate of mortality, the likelihood of you dying of something in the next year, has gone down. That's generally good. But death is probability 1. Sorry, guys. Death is probability 1. And so we can ask, what is the likelihood that cancer is going to be the cause of death on your death certificate? And that keeps going up. So the United States right now, it's 1 in 5. Sweden, it's 1 in 3.5. Netherlands is 1 in 4. And you can see why. Notice the overall death rates for just about every major source of mortality has gone down dramatically. And then you look at cancer and you see a flat line. So we as a group aren't keeping up our job. I think one of the reasons we may not be holding up our end of the deal, and this will be part of then the topic of my talk today, is it actually starts with how we even define cancer. So up above is the standard definition of cancer you'll find all over the place: a disease of uncontrolled division by abnormal cells. And what I'd like to propose in the definition below that we recently published is that cancer is a disease of uncontrolled proliferation, that's fine, by transformed cells, transformed, not abnormal, transformed cells, subject to evolution by natural selection. It's that subject to evolution by natural selection that is the devil in the details. And so at least in my lab, the things that I'm interested in, my colleagues, it is evolution by natural selection that drives my interest. And it's an open question whether embracing natural selection as a key component of cancer will help us. Part of the motivation is the evolution of therapy resistance, explains most therapy failures. And finally, cancer will be each of our most personal experience that we will ever have of evolution by natural selection. How does this perspective help with therapies? And we saw that in Bob Gatenby's talk. And I would then suggest to you that cancer therapy is an evolutionary game. It's an evolutionary game. As soon as the physician, the caregiver administers therapy, if you do not kill them all, it is game on. The cancer cells will evolve a response, and often that response is worse than what we started with. So here's a dream worth thinking about. Could it be that we actually have all the drugs needed right now to be able to cure or contain almost all cancers of all stages. If that's true, then our challenge and problem and opportunity is how we deploy them. And what it means then, if it's an evolutionary game, we're entering into an evolutionary chess match. And it's really a matter then of coming up with the moves. And so I would suggest to you then that perhaps right along with what you might call the current drug development, what you might call the world of small molecules, perhaps now is time for algorithms as drugs. So what I'm going to do, cancer is an evolutionary game. I want to present some tools of the trade, and then this anticipate and steer in evolutionary therapies. We saw that with Bob Gatenby. I go along with this pretty quickly. I love game theory, and always liked it from the time I was in college. At that time, I had to learn it in economics. And there's lots of ways of describing game theory, but I like to think of game theory as simply that field of mathematics in which you are trying to optimize when your best choice depends upon the choices of others. And in fact, when you think about that, my best choice depends upon the choices of others. John Nash had it right when he said life is a game. Games have players, rules, strategies, and payoffs. And so what does that mean when we get into the world of cancer? Well, in terms of game theory, it was my game theory mentor, Tom Vincent, who tragically died of pancreatic cancer in 2009. He was an aerospace and mechanical engineer and was particularly interested in evolutionary games. And evolutionary games are particularly interesting because they draw upon Darwin's postulates. Heritable variation. Like begets like, but with boo-boos. Like begets like, but with boo-boos. You go to the maternity ward, you get a baby, and somebody says, oh, wow, look at that. It's got Uncle Fred's nose. Oh, that's too bad. Has a little bit of Aunt so-and-so's appearance. But nobody says, oh, crap, I just had a baby sloth. We were really hoping for a giraffe. I wonder if we can trade it in. So heritable variation, like begets like, but with a few kind of boo-boos around it. Second is a statement of ecology, the struggle for existence. All populations have the capacity to grow exponentially under ideal conditions. However, no population can grow exponentially forever. There's limits to growth. It's a statement of population ecology. And then finally, the genius is putting it together. And that is variation influences the struggle. So as my academic great-granddad noted, or was, it is the ecological theater and the evolutionary play that is best described here. How do we put these postulates into action? Heritable variation just says organisms possess some set of what is evolutionarily feasible. We'll call that U. We'll let it be a continuous set. It doesn't have to be. There has to be a struggle for existence. We'll define fitness through G, per capita growth rate. And all it says that at some point, there will be some level of population size. Who knows what that is necessarily? That may be carrying capacity, it may be way beyond carrying capacity. There is some population size such that above that population size, per capita growth rate declines with population size. Then we bring it all together in this function, this fitness generating function G, in which we say, okay, my fitness is a function of my strategy, and then the strategies of everybody else. And everybody else is the vector of strategies that are already present in the population, their population sizes. And of course, that's the essence of game theory. The essence of game theory is identifying the consequences of the environment, including the strategies of others, on me, the focal individual. But of course, me, the focal individual, is part of the biotic environment of everybody else. So it's always that frame of reference. Who's me? Who's you? And so in this case, V then is our focal individual, whether that focal individual exists or not in the population. That allows us to understand what's going on. So with that formulation, we can now ask the question then, what does this lead to? What kind of dynamics can we expect? And they can be described quite simply. The ecological dynamics are fairly obvious. The change in population size is just per capita growth rate multiplied by the population size of those individuals with that strategy. So we just substitute UI for V, and we have their fitness function. Strategy dynamics, the standard, you see this in adaptive dynamics, Fisher's fundamental theorem of natural selection, quantitative genetics, Falconer's genetics, have noted that in general, you can approximate a change in the strategy of a population, the trait value of a population, as being proportional to and driven by the slope of the fitness function, the adaptive landscape, multiplied by some evolutionary speed term. And this evolutionary speed term can represent the amount of heritable genetic variation, additive genetic variation, epigenetic, it can be phenotypic plasticity But roughly speaking, then we can track evolution of each of the strategies in the population using this particular function. If one doesn't want this sort of adaptive dynamic, you can always have an invasion structure. You just toss in individuals into the population, or you toss in invading populations with some new strategy that isn't present. A bit like how invasive species might build up a community of birds on the Hawaiian Islands. The recipe for an evolutionary game under this schema is pretty straightforward. Pick your favorite model of population ecology. Decide which parameters in this model are influenced by the evolutionary trait of interest. Place bounds on that evolutionary trait. Imagine how that evolutionary trait influences the fitness function, and presto, you have a G function, you have an evolutionary game. Here's just one example, just to kind of illustrate some of the phenomenon. Here's our friend Lochte-Volterra competition equations up there. And all I've done here is made carrying capacity a function of your strategy. So your strategy influences, say, resource availability, carrying capacity. And then this really awful looking function here says that the competition that I experience from others is a function of my trait, the traits of others. And the way this function is constructed is it says like competes most with like, but there's a bully term in there. It says if I am bigger or have a more extreme value of the trait, I have a greater impact on those with a lesser value than they do on me. And so this is just to make an evolutionary game that illustrates many of the interesting properties of games. The first property is you can then study the dynamics on an adaptive landscape. However, the adaptive landscape itself is dynamic. And that perhaps is the most interesting thing about evolutionary games. So each of these frames, I want you to imagine that this is fitness as a function of your trait. And that's whether you're in the population or not. This is our kind of our virtual focal trait. The circles, at any given time, the circles represent the current strategy of individuals within the population. So the circle is reality. The circles is what you can actually observe in nature right now. And then what happens is we can plot the adaptive landscape. Several things you'll notice. The circles are always at 0. What that means is we've allowed the population size to equilibrate at its carrying capacity so that fitness is 0. So that just tells us we're at ecological equilibrium. Then the landscape itself tells us, are we at evolutionary equilibrium? Of course, we're not in the first frame. And as we move to the second frame, we move up the adaptive landscape. But of course, any change in the adaptive landscape and the trait will change the population size and put us right back at 0. Right back at 0. And so this process just continues and continues until at the end of it, we reach a point that is both ecologically stable, 0 fitness, and it's evolutionarily stable because we're on the top of the adaptive landscape. And so these landscapes can be exceedingly dynamic. One of the outcomes that was observed, Peter Abrams, who was here at the University of Toronto, my own lab back in 1992, the adaptive dynamics folks, was that this process, like that model I showed you, this hill climbing exercise can actually put you at a convergent stable minimum. So back in the 1990s, that was kind of an exciting result, that evolution by natural selection could actually evolve you to a point of maximum disruptive selection. You get a convergent stable minimum. And this has now been observed by many as a potential source of biodiversity. This could be true for cancers or any system that would allow speciation. Or you can have a situation where you've got a couple of peaks that are convergent stable, but they're not the absolute maximum. Or you may have the adaptive landscape. That model I showed you can generate a system that looks like this, where you got 3 strategies coexisting that are at maximum of the adaptive landscape. So one of the key concepts, Maynard-Smith, is evolutionarily stable strategies. Evolutionarily stable strategies just says when everybody's doing those strategies, no alternative strategy can invade. You'll notice that's Nash. Interestingly, Maynard-Smith never really knew about Nash, but in fact, a key element of his definition is Nash. There's the ESS maximum principle. This is just a long-winded way of saying that at an ESS, the trait values must be at maximum of the adaptive landscape. There's an example of such an adaptive landscape. But then there's a question of convergence stability. Can you actually evolve there? And that's what's kind of exciting about evolutionary game theory. There's a lot of stuff going on behind the curtain. So can you actually get there? Will evolution by natural selection drive you there? And then the third one, this was Joe Opoulou, discovered this property of evolutionary stability. If I'm rare, can I invade? So if I'm not at the ESS, if I'm rare, can I actually invade at the ESS? This is neighborhood invader strategy. Aren't these cool? There you are. There's the conditions on the G function for it. But let's just take a look at what it looks like in terms of the adaptive landscape. So here's a case. We have an ESS. We'll let that be the peak. Here's a case then where it's convergence stable. If I perturb the population or the trait value away from the ESS, notice the adaptive landscape drives me back. But notice the ESS strategy can never invade. It can't invade. So this would be convergence stable, non-NIS. Why does that matter? In a system like this, evolution by natural selection will never get there. It will get exceedingly slow. And there are models and people put together models that have convergence stability, but not NIS. Here's an example then where one is both convergence stable and it's NIS. In these cases, we can expect evolution by natural selection to get us there. It will actually get us to the ESS. So evolutionary stability, that was just kind of a quick run through of things that get me kind of excited. Comes down to ESS, NIS, and convergence stability, produces 8 combinations. It turns out in our reality, unless you're writing a science fiction book, only 6 of them are possible. Only 6 are possible. And so these attributes of evolutionary stability allow one to understand a lot of the personalities of models and how they might proceed. So what of cancer? I'd like to suggest to you cancer is a game. The cancer cells themselves are the players. Their heritable traits, phenotypic plasticity, epigenetic possibilities, all of those represent their strategies. Their payoffs are very straightforward. Proliferation and survival. Wow. And as an ecologist, that's just about as simple as it gets. And then the tumor microenvironment sets the rules for this system. I'm now going to suggest how can we use this once you understand the game. So I'm going to describe to you squirrel hunting as a Stackelberg game. Those are leader-follower games, and I'll explain a bit more about them. But I think it also describes current therapy and where therapy can go. So anybody in here have dogs that like to chase squirrels? Any squirrel chasing dog people here? Cool. Now, an attribute of many dogs, now some are very clever dogs, but many dogs, when they chase a squirrel, they point directly at the squirrel. They point directly at the squirrel, run right towards the squirrel, and of course the squirrel runs for a tree. And you see this wide arc. Any of you doing kind of time-dependent differential pursuit evasion games will recognize that's not a great strategy. It's not a great strategy. You run in a wide arc, and then squirrel runs up tree. Now, if the dog is fast enough, or the squirrel is far enough from a tree, it doesn't matter. Even that strategy will work. Now, a coyote, a clever coyote, or a clever dog, unsurprisingly anticipates the tree to which the squirrel is going and cuts the squirrel off. Kind of interesting. Furthermore, which I think is really cool, sometimes squirrels have 4 or 5 trees they could go to. Think of them as resistance strategies. They have 4 or 5 trees they can go to. And the squirrel might not even know which tree it's going to initially. There might not actually be a biomarker available at that moment to know which tree the squirrel is going to. Does anybody in here know what a coyote does in that case? Any? No? What's that? Well, that would be cool. No, what it does is a fake. The coyote does a fake. It gets the squirrel to commit. It gets the squirrel to commit. So what I'd like to offer to you guys, which I think is, I would say current therapy, or at least much of current therapy in cancer, you heard it here, I get in a lot of trouble, is like stupid dogs. Wow, that wasn't very kind. Anyway, very sophisticated. In other words, what we do is we measure right where the tumor is now, right where the cancer cells are now. We get down to the nanometer, genetic, all the characteristics of the cancer. It's amazing. And then we blow that spot up for the next 6 months, 18 months, 20 months, whatever. And if there's a big hole, congratulations, there's a dead squirrel at the bottom of the hole, but most of the time the squirrel is gone. And that's the essence then of Stackelberg evolutionary games. I will chug along as best I can on there. Thanks. So Stackelberg evolutionary game theory is this idea of where you have a rational leader who can maximize some objective function, and then you have a resource, a pest, a microbe, a cancer cell that basically follows the rules of evolutionary game theory. This has been applied much of in my previous life. My first entree into Stackelberg evolutionary games was in fisheries management. And then later it was in pesticide management, and now it's in cancer. So cancer therapy, we're going to argue, should be, can be, and should be a leader-follower game. What does it kind of look like in practice? To give you an idea, let's say these are best response curves. This is the level of resistance in the cancer cell. This is the level of treatment. This is just a simple illustration of what goes on. So let's say right now, this is the best response curve of the cancer cells. This is what the cancer cells will do eventually in response to any treatment. This is the best response curve then of the physician on there. And if you just keep chasing the cancer, like we often do, you'll actually wind up at a Nash equilibrium up here, where the two best response curves cross. But if you can anticipate what the cancer is going to do, you know it's eventually going to wind up on this line. So if it's going to wind up on this line, you can pick the point on that line that maximizes your outcome. That's the Stackelberg solution for this. What this has led then to is new approaches to therapy. I'd say right now, the two very common ones, the magic bullet, coming up with the right kind of immunotherapy, coming up with the right small molecule that will cure that cancer most of the time under most circumstances. Usually, these magic bullet approaches run about 10 years. You know, it was hormonal therapy, chemotherapy, targeted therapy, first rounds of immunotherapy. Now it's the world of CAR T-cell therapy and whatnot. And they've left us with amazing drugs, but they never quite live up to their promise because evolution by natural selection is smarter than we are. The second approach is just to kind of mix combinatorics. Let's take these drugs, combine them. So the third way then is a variety of evolutionary therapies. I'm not going to go into all of these. Bob talked very nicely about competitive release therapy, adaptive therapy, but these are the current ones. The ones in black are the ones that are currently in clinical trials. This one, double-blind therapy, is getting really close to being in a clinical trial. And so I just want to give you a real quick walkthrough of this in action. I'm just going to take 3 more minutes, and I promise let people get to coffee on there. And so pediatric rhabdomyosarcoma, we saw 2 nice examples with prostate cancer. Those are just a bunch of old men worried about their prostates. Let's get into something that makes me really sad. This is still the cancer that makes me cry. Just thinking about it. Pediatric rhabdomyosarcoma is exceedingly rare, thank goodness. Maybe 250 children and young adults in the United States will have this disease or succumb or have this disease happen to them. But when it happens, they have a 3-drug therapy that works like magic. Otherwise, a painful disease in the bones magically disappears. 5% of those patients are cured. 5% are cured. The other 95% will go on and die in about 18 months. In about 18 months. And it's a really horrible way to go. It's painful. It hurts. The drug toxicity is really ferocious. So Damon Reed was interested in, could one do this as a clinical trial and use evolutionary therapies? It's actually a 3-drug. The current therapies are 3 drugs, and they have not changed in 30 years. This disease is an orphan cancer. It's not worth big pharma. It's not worth it for the number of patients. The drugs have not changed, these 3 drugs. And so this model, working through the literature and Damon Reed's expertise, constructed then a model in which you have 3 drugs, M1, M2, M3. You have 2 resistance strategies, V1 and V2, because it was thought then that the same resistance strategy works on these 2 drugs versus the third. But using this model as the basis for it, then designed a 4-arm clinical trial. And this clinical trial is actually happening right now. There's standard of care. There's an adaptive therapy, like you saw with Bob Gatenby. Add therapy when the disease is above a threshold, stop it when it goes below a threshold. The other is we call first strike, second strike extinction therapy, hit it really hard up front, and then quickly switch to another therapy, whack it and stop and see what happens. And then the top line is an augmented first strike. Take those 3 drugs, swap one of them out, add an even more lethal dose, but hit them for a short amount of time. So taking one set of parameterization, this is an example of what might be expected under these 4 treatment arms. The red line represents an extinction threshold. Arguably, if you get below this line, you're cured. Notice the adaptive therapy does not have an extinction threshold because adaptive therapy, by its very definition, never intends to drive the tumor burden below a certain level. Made a whole bunch of virtual patients, and this then became some of the sort of rough expectation. Ignore the colors. Each of these arm A, B, C, and D is arm A, B, C, and D. These are the cure probabilities from them that is being estimated. Now, for this clinical trial to be implemented across a large number of cancer centers, Moffitt does not see many of these patients. The entire clinical trial allows for the physician to present the 4 options to the patient or the patient's parents, and then they decide what arm they want to be on. So it's not a true controlled, it's not a double-blind study, it's a choice study. It's just offering them the opportunity. They can go read the paper. They can have the paper and see what's here. But I just want to let you know that these are real people. These are real people. They're not abstract. And the model then is at least influencing or suggesting ways to go. So here is a woman in Tampa, 26 years old. This is the sort of standard sorts of events. You get growing pains, you get swelling. You hope it's nothing serious. It turns out to be this horrible disease. This woman decided she did not want the toxicity. She did not want the toxicity. She wanted the adaptive therapy. She wanted the adaptive therapy. And right now, this is showing you some of the course of her disease. Now, here's the on-off therapy. I'm happy to say, I need to update it, she's still alive today. She's going up and down. Everything about the model says she will still die from this disease, but our goal is to get her to 3 years. 3 years for a young person like that. But the other aspect of this is this line here is a measure of quality of life. This is a patient-reported outcome of quality of life. And under this regimen, you see an improving quality of life. So, interestingly, even though this woman knows she is going to die of the disease, she has eyes wide open. She's actually pretty pleased. How's that for courageous and amazing? Thank you very much.